Here is my plan for you. In class on Thursday, we were able to get through actually forming electron configurations using the periodic table. I really wanted to get you guys to that point. Okay? The start of this video will have information that all of you need. Okay? It's about the 3 rules we use to actually create electron configurations. You already kind of know how because I showed you, but these are just the principles behind why it works the way it does. Okay, so this is the why, a little bit of the why, and you need to know a little bit of the why. So if you seem to understand class on Thursday and you're doing fine with the worksheet, watch this first part and be done. For the rest of you, once I go through the rules, I'm going to do more practice. Okay? If you're having a hard time in class at the end Thursday, watch the practice and then watch it again. And then pause it and try it on your own. And if you don't get it, watch it again. And watch it 10 more times. Watch it 20 more times. You have to get this. You have a test on Wednesday. You cannot wait. It's now or never. Okay? So electron configuration is when you actually write out the whole like 1s2, 2s2, 2p2 type thing. You're mapping where electrons are. They're no longer in rings. They're in orbitals. There are 3 rules that tell us where every single electron goes. There's Hunds rule, there's the Aufbau principle, and there's the Pauli exclusion principle. The Aufbau principle you already used already. It's what you guys used with the Bohr model. When you made your rings, you always filled the innermost energy level before you went to the next one. And that's the Aufbau principle. Electrons will always reside in the lowest energy orbital before moving up to the next one. That's why electrons go into the 1s orbital before they go into the 2s orbital. The 1s orbital is lower in energy than the 2s orbital. Now remember, your periodic table tells you this order, and it tells you that 4s will come before 3d. There is a shifting that happens because the 4s orbital, that S-shaped orbital, is so small and so stable, it shifts below the d, which is very big and unwielding. So if we do hydrogen, which has 1 electron, that 1 electron will go in the 1s orbital because it is the lowest energy level available. The Pauli exclusion principle is actually the person who discovered that electrons are going to spin oppositely and be paired together. Okay, again, that was part of Schrodinger's equation, but Pauli exclusion principle was kind of the one who originally found it. Okay, so 2 electrons will fit in each orbital, and those 2 electrons will be spinning in opposite directions. So again, S can hold 2 electrons because it's 1 orbital shape. P can hold 6 because there's 3 orientations. D can hold 10 because there's 5 orientations. F can hold 14 because there's 7 orientations. When we actually draw electrons, we usually draw them as arrows, okay, single-headed arrows. So that is an electron spinning up, and this is an electron spinning down. Okay. So for example, this could be the 2 electrons in the 1s orbital. 2 electrons spinning in opposite directions. You would never have 2 electrons like that. Okay, they have to spin opposite. Remember the S, P, D, and F has a relationship with your periodic table. You have the S block, the D block, the P block, and the F block. The first column of S is S1, then S2. If you go to P, it goes P1, P2, P3, P4, P5, P6. D, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, F through 14. Normally you know which energy level you're in based on which row you're in. So for example, this 2p that's on there is in row 2, and it's in the P block. For the D, it's the row it's in -1. So it's 3D instead of 4D. And then F, it's -2. So that's 4F instead of 6F or 5F. Okay. So the Aufbau order of energy levels from lowest to highest is given to you from the periodic table. If you simply read the periodic table left to right, top to bottom, moving up with atomic number. Okay. So this is the order of the electrons that I had on the board today, except with the electron information also. So this particular electron configuration is representing, gosh, I don't even know, representing whichever one is in this 7p location. Okay. Obviously, you know from today, we won't usually write one this long unless we're dealing with element down near the bottom of the table. Okay. The last rule is Hunds rule, and how Hunds rule works is, if you remember p orbitals, there's 3 potential orientations. I said in class today that sublevel, that energy sublevel with 3 p orientations, those actually all have the same energy. They're just oriented differently in space. And Hunds rule is, when you have electrons available and they're filling into what's called degenerate orbitals. Degenerate orbitals are orbitals of the same energy. Electrons will go in actually all spinning in the same direction before they'll pair up. So the most stable configuration is a half-filled orbital or a full orbital. Okay. We call this the empty bus seat rule. Imagine getting onto a bus. You're going to try to sit in a seat that doesn't have a person in it before you pair up. Same with the electrons. They want space, right? They repel from one another. They don't want to share space, but there is a natural stabilization that happens once they're all paired and spinning oppositely. So one way we sometimes represent electrons, I said, is up and down arrows. So let's imagine these 3 lines represented the 3 2p orbitals. Let's say I was trying to put 3 electrons out in 2p. Those 3 electrons would go in all spinning up before I paired them up spinning down. Hunds rule is going to affect us when we look at the exceptions on Monday, because the exceptions are based on the element trying to achieve a half-full orbital or a full orbital. Okay, because all 3 electrons spinning parallel or all 3 spinning opposite, or all 3 full, gives it stability. So you've seen this now. I showed it to you in class, what electron configuration looks like. Energy level followed by orbital type followed by number of electrons. If you understood on Thursday, stop the video. Go do the practice. I'm done with you. I'm done with you. But if you had a little difficulty and you want to see this applied again, stick with me. And let's say I'll do 4 examples. Okay? You gotta practice. Okay? You gotta practice. So let's have our first example be aluminum. If you want to, pause the video now and try it on your own, and then come back and see if you did it right. Okay? So if you look at aluminum on your periodic table, I have it on my phone. Aluminum has the atomic number 13, which means it has 13 electrons. Okay? So I'm going to put 13 electrons out on my periodic table. Starting in the upper left corner of your periodic table, you're going to place electrons in the lowest energy level available until your electrons are gone. The first energy level you run into is always the 1s orbital. And in the 1s orbital, you can fit 2 electrons. Are you done? No, because you have 13 electrons, and right now you've placed 2. So moving on to the next closest energy level, you're in 2s. That can hold 2 electrons. You're still not done because you're at 4. So you're going to go forward, and if you move across the periodic table, okay, after your 2s, you're at atomic number 4. Go to atomic number 5. You're still in row 2, and now you're in the p block. Okay, so you're going to be in 2p. 6 electrons fit into 2p. Now you're at 10, so you're still not done. Going from 10, find number 11. That's the next orbital you're in. You're in row 3 in the s block, so you're at 3s. And there's 2 electrons. You're still not done because now you're 12 and aluminum's 13. So you got to go to number 13 where aluminum is. And that aluminum is in 3p. And it only has 1 electron in the 3p orbital. It shouldn't surprise you that the last orbital that we hit is a p in row 3, and there's 1 electron. Aluminum is in row 3, in the p block, and in the first column. Let's do another one. Okay. That was aluminum. Let's try something different. Let's try molybdenum. No, let's not do molybdenum. let's try palladium. It's number 46. Okay, palladium, it's number 46. It's PD. 46. You start these all the same way. Go to your lowest energy level and place your electrons there until you get to all of your electrons being placed. The lowest energy level is 1s. We'll put 2 in there. Okay, so now go to number 3. 3 is in the 2s orbital. And we'll put 2 in there. And then moving across to your 5th element, that's 2p. And you can fit 6 in there. And then you'll go 3s, and you'll fit 2 in there. And then you'll go 3p, and you'll fit 6 in there. So now you're at, 6, 7, 8, 9, 10, 18. So go to element number 19. You're in row 4, and you're in the S block. So you're 4s, and you can fit 2 in there. After 4s, you're now in your D block. Remember, your first D row will always be 3D, row minus 1. And you can fit all 10 of them in there. After 3D, you're in row 4 and in the P block, so that's 4p6. Moving down your periodic table, now you're in 5, 5s2. Okay, move over, now you're in the D block, okay, and it will be 4D, because it's row minus 1. And then the question is, how many? Because palladium is in row 4, right? And it is in column number 1, 2, 3, 4, 5, 6, 7, 8. So palladium has 8 electrons in the 4d orbital, and your electron configuration is complete. Right. Let's do another example. Let's do strontium. Strontium. Strontium is number 38. Okay, strontium is number 38. So, you always go from the lowest energy level up. First energy level you'll hit is 1s. You'll put 2 in there. Then you'll go to element number 3, which is in the 2 row and in the S block. So 2s2. Moving across, you'll hit still row 2 in the P block, and there's always 6 in P, 2 in S, 6 in P, 10 in D, 14 in F. Count your columns if you can't remember. 2p. Then you're in 3s, and you can fit 2. Then you hit 3p, and you can hit 6. And if at any point you're like, wait, am I done? You can always check. Let's count. 6, 7, 8, 9, 10, 11, 12, plus 6 is 18. I'm only at 18, I need to be at 38, so I'm not done. Moving down to for element number 19, that's in the 4s, and I have 2 of them. And then I hit 3d, which can fit 10, 4p, which can fit 6. So how many am I at now? I was at 18, so that's 20, 36. Oh, I'm so close. 36. I just got to be 38. So 36, go over to element number 37. That is in your 5s. Okay. And how many am I going to fit in there? Well, it's actually going to fill. And you're going to have both of them in there because of where strontium is on your periodic table. Okay. I think that's enough practice. I think you've seen this now a few times. Practice it yourself. And if you can't do it, come back and watch this again. It's all about placing electrons in the correct energy level based on the location of the periodic table. Okay. On Monday, you'll see a way to do this shorthand so you don't have to write all this out all the time. You'll see ions and you'll see exceptions. Okay. Just do it. Practice. If the videos aren't helping, read the book. If the book's not helping, come in Monday morning. Okay, get me early and make sure you get this. I really want you guys to be successful. Okay? Have an awesome weekend. I'll see you soon.